Welcome to our talk. Talk today by myself, Mary Grygleski, and Fabio Tiriticco. Today is an interesting emerging topic presentation called Retrofit Your Legacy Java App with a Reactive Flow Pipeline. We'll take a look at how Reactive can be applied to transforming an old traditional legacy Java app. And this is our agenda for today. We'll have a quick introduction, and then we'll go into talking a bit too about a bit of history as kind of setting up the stage as to why we have this talk, discussing from the perspective from an enterprise JVM applications point of view. And then we also explore into a bit of the complex problems in today's world that's evolving, that's becoming more and more complicated, needing more and more data. Everything is just come in bulk. We have so much to sort through. So what would be a good approach is what we're proposing here, which is the fourth section is about some solutions that we can be using and it's basically leveraging on the reactive approach. And then Fabio will then take us into an in-depth look into an experiment that we have done, and mostly merits to Fabio, who spent a significant amount of time working through some of the inner things. And so that will be Fabio area. He will spend more time with you on that. And then after that, we will come together and give a conclusion to this whole experiment on the reactive Java kind of experience that we have. So, all right, so let's begin. A quick introduction. I'll just since I'm talking, let me introduce myself. I'm Mary Grygleski. That's my Twitter handle, and I'm a senior developer advocate at IBM in the Java, open source, and cloud space. I'm also, by night, president of the Chicago Java Users Group, as well as a few other user groups in the Chicago area. So now to you, Fabio.
Yes, hi everybody, and thanks for having us. My name is Fabio Tiriticco, and Twitter handle is TicoFab. It's a lot easier to pronounce than my family name. And I am based in Amsterdam, where I work as a software engineer, now currently actually in an engineering manager position. And I am the founder of this community, Reactive Amsterdam. So yes, the topics of today's talk are really, really dear to my heart.
Thank you, Fabio. So with that, without further ado, I'm going to start. So why, right? And I've been speaking at a lot of conferences, and so has Fabio with a deeper experience in reactive too. And I'm sure, Fabio too, like myself, we've constantly been asked by our audience as to, well, how can reactive be of use in today's world? So one aspect that we have been exploring into is really looking into enterprise JVM applications. These are applications that are powering the world's huge kind of backend applications in production, in big financial places, in insurance company, in manufacturing places, you name it, they are there. So their mission is actually very important for the company. They do a lot of things on, for example, very typical ones is like e-commerce systems that essentially you have customers trying to shop for something, catalog, and then you order. To order, as we all know, is not a simple thing. And then, of course, with this order, and with today's world, we are not just paying by cash, and we are also doing credit card, or now even more like, kind of what cashless payment, or what cardless payment, I'm sorry. And so all these things, they are very complicated and require a lot of security and all these things. And as you can see, is really complicated. But the traditional way of doing things is that before hardware has been able to get caught up, when we're having single CPU or having like parallel processing of multiple CPUs, but essentially kind of, like a single thread handling per CPU type of scenario. Um, Applications were developed in a very monolithic fashion. So everything too we could be processing is all in the same JVM, if it's taking Java. And they are all like doing things within the JVM, let's say order entry. And if you have an order, you need to talk to send your order over to your credit card, verify all your transaction. They will actually essentially hold up a thread and you just like have to sit there and wait. And that type of, it's just an example of some of these monolithic applications in their runtime, the effect of how it affects the whole system is just not designed to be very scalable, not very flexible at all. And not only that, on the design side, we run into that problem in runtime. But the thing is too, is that we also rely on a huge operation teams to help us too with the building part, not only building. In the testing phase too, we will be like having, a different development version of your code, or have your QA running a separate version. And then you have certifying all that before you go into production. Then, so overall too, the maintenance of such application is very high. And it's also not very flexible. It almost seems like the world must stop if you need to upgrade any part of your system. And that's kind of like the whole kind of issue with it. And of course, too, the data aspect too, is kind of like hard for it to be kind of like go through different states without being easily able to get updated the state changes between these different parts. So let's go on. And of course, too, not to mention the fact is that there's also the concurrency aspect of processing that present itself a lot of challenges. So those are kind of like some of the traditional enterprise applications that we can kind of think of using a reactive approach to solve. Then we talk about the solutions that we're proposing is to use this reactive approach. Is that in today's world, then of course it's microservices has already been popular in since I'd say in the 2010s kind of time frame. And so those are solutions of using this reactive approach. And actually microservices itself too is kind of perfect for letting the reactive or be adopted by the reactive way. They kind of both are kind of work together very well. A reactive system itself is by nature not tightly coupled too. So microservices is like a perfect kind of architectural approach that reactive systems can use. Oh, actually, I should also add too is that also the serverless aspect to it. It deals with the deployment part too, and in the serverless cloud native world too, it's also very suited for this reactive approach. And of course too, with microservices, everything kind of broken out and no longer like, all together, then you can essentially do your upgrading without one part can be down while other parts are still running. So that kind of is very, very conducive for the reactive approach. And of course too, there's also the traditional operations part is no longer the case. We're kind of using modern DevOps and infrastructure to for the deployment, building, continuous integration, and deployment part. And now too, if you think of reactive too, is basically enable concurrency without us, the developers, still having to worry about the mechanics of threading concern, because all of the threadings are now being handled by the libraries, by the reactive framework or libraries or toolkits, so that developers can then focus on actually the business operational side. Now, the thing is with using reactive approach is basically we're proposing is to build and transform some legacy applications. We're identifying parts of it and allowing the data to be flowing through different pipelines. And that's the area that Fabio will be demonstrating for us is to a case in which we're building using different implementation of a reactive pipeline and different reactive libraries to implement this pipeline. And so I will pass the baton over to Fabio to talk about this particular use case.
Yes, thank you very much, Mary. What we are going to look at is this hypothetical situation where we're talking about some data pipeline and there's going to be some processing happening. The first legacy processor will read, consume data from the first Kafka topic, and then the second processor will do some additional processing on it after it has received the output of the first processor. And finally, the second Kafka topic will be where our process data will end up. And what's important is in this entire pipeline, we are using concepts coming from the Reactive Streams idea, where Reactive Streams is a standard that has been part of the JDK since JDK 9, I believe. And one of the most important consequences and benefits of using this standard is back pressure. So what we'll see is that the entire process only does actual something if there is demand from downstream. So in this concrete example, let's say if the legacy processor number 2 doesn't have enough capacity to process all the potential incoming data, the first processor, legacy processor number 1, will be reacting to this situation by simply stop sending data and awaiting for legacy processor to be ready to process more information. And this is crucial in large systems where many pieces interact with one another, as fast producers might boggle down slow consumers. And so in order to avoid this sort of overflowing situation, we have these pipelines that employ back pressure all the way up to the source of the data. And now let's go look at some code and some demo. Here we are. You should be seeing my screen now. And what you are seeing now is, in fact, the GitHub repository with the code for the demo that you're about to see. As you can see, there's these 2 legacy processor 1 and legacy processor 2 are our projects. And then there's 2 other folders. One is about infra, is a simple Docker Compose file that will spin up our Kafka infrastructure. And sources producer is a project that will simply put some random data on Kafka, so the first legacy processor has something to consume. Now let's see this in action. Here we are. There's our infra directory. Let's spin up our infrastructure. This is going to start our entire Kafka backend. Yeah, there it is. Now we have a running Kafka cluster on my local machine. And so let me start the sources provider, which will start push data into our Kafka topic. This is going to be just, let's see, there it is, 1 record per second containing just that specific timestamp, as you can see. And this guy is just going to keep producing as we go. So let's first look a little bit at the code before we started. What you are seeing now on screen is the implementation, the actual starting point of the first legacy processor. It's in Scala. And it uses a reactive stream implementation called Akka Streams. Akka Streams is based on Akka, a product from Lightbend, an open source product from Lightbend. And the idea of Akka Streams is that implements indeed the reactive stream specification. So there are a lot of different connectors that we can use in part of Akka Streams. In particular, here we are going to use the connector that allows us to connect to a Kafka topic and consume events from it. And see this little snippet here, this is the entire thing, the whole thing that we really need to look at. What this processor is going to do is going to, okay, after instantiating some configuration setting, like which topic we are going to submit to listen to, here we are creating our stream, which starts considering our Kafka topic as a source of items. And then for each item that comes in, we are first simulating some processing. In this case, we are just extracting the string value, and then a little step here to convert the string into bytes. And then we are going to put this data into a RSocket sink. Now, a little introduction to RSocket is necessary here. RSocket is a protocol alternative to HTTP. So at the same level it's an application level protocol, basically built with the reactive stream concepts in mind. So there are solutions that leverage the reactive streams idea into HTTP, making it a back pressure enabled transmission of data across services, but RSocket is born with it. And this is all you need to know really for now. But RSocket is really an interesting project. In fact, RSocket stems from reactive socket. That's what it was called in the beginning. And it's above TCP, so it makes a good candidate for intercommunication between two services. And in this case, this legacy processor one, what we have done is, let's say this process item function method here represents a legacy type of processing. Maybe we are dealing with indeed some legacy logic that we have and we don't want to change, and all we want to do is wrap it inside a stream. And then the data that comes out of it, we are going to offer to this RSocket sink. We are going to look at the implementation of this a little bit later. If we look for a second at the second legacy processor, which you are seeing on my screen, this is a Java application, which again, it will create a Kafka producer in this case, because the output is producing data onto a second Kafka topic. And then this code that you see here is about, let's say, this block here is about creating a RSocket receiver. So once the first legacy processor finds a valid connection to the receiver, it will start pushing data through. And what happens with the data that we receive is right here, is this bit. For each item that we receive from the first legacy processor, we are going to extract its string content and simulate some work. This is again simulation of some legacy processing logic. This processing actually is maybe a little interesting to look at. It's just down here. It will basically make our machine and our thread sleep for a random number of seconds. We'll see later why a random. And after we are done processing, we are going to publish the data onto a second Kafka topic. What's interesting to notice here is that when only at the moment when we return from this method, once the execution of this logic highlighted now has completed, this is going to be the signal to the first legacy processor that we are ready to receive more data. And this syntax here, flux.empty, you are probably familiar with it if you have used the Project Reactor or Spring Boot-esque applications. You are probably familiar with this logic. And this is all I want to say for the moment about this legacy processor. Let's try and give these two guys a spin in this window here. So let me first start. Let me just check that our sources producer is still producing data on Kafka. So let's spin up our first legacy processor. Now, this processor has started and is trying to connect to a RSocket receiver, but at the moment there's none running. So what's interesting already to notice is that because there is no server running, then this entire stream is not consuming anything because this particular component is not asking for anything to consume. So by going all the way back to the source, we are not consuming anything from Kafka. This consumption will start when we trigger the second legacy processor. What we should see, if the demo gods help us, is that the first legacy processor will connect to the listener and start consuming events from Kafka. There it is. So here, what you could see is that when an item is received on the second processor, then there is this random delay. So you see 2 seconds, 3 seconds, and the first processor is only reading messages from Kafka as there is availability from the second processor. And so you see that they really go hand in hand. The entire thing is protected in this sense. We are only consuming data when there is some need for it. And I just want to, this concludes our demo. I just want to spend one more minute for those of you familiar with Akka Streams. It's an incredibly powerful ecosystem, incredibly rich. There are Kafka connectors, HTTP connectors, or connectors to connect to basically most of your potential technology underneath in a reactive way. But interestingly enough, there isn't an official connector for RSocket. So what I have done, I have created these two RSocket sync and sources, get an inspiration. There is a blog post actually on the Lightman website, which I used as a inspiration and then built on top of that. This code you see here is the RSocket sync that we are using. And the idea is this is the area where we create the connection to the RSocket receiver. And then what I want you to look at is basically two things. This method here that we have overridden on push lets us write the logic of when we should retrieve items from the stream and when we should get then the next one. So in this case, this grab is the signal to grab an item from upstream, and then only so we are grabbing some payload here. Here, this is the line where we are sending the payload further, and then only when there is a request, we are asking for a new item that will be triggered from above. And the code is online, so you can look at it. This is all for our little demo, and now I would like to share with you a couple of conclusions about this experience from building this pipeline. So the good things and the bad things I found. Well, first of all, I have some experience with reactive streams already, but if you haven't been exposed to them, to this kind of a standard, it really is incredible. It enables you to work with different technologies, not only on the JVM. You could have a reactive stream implementation in Python, for instance. Why not? And still keep the streaming semantics of back pressure all the way through the pipeline. But something that is not great is that different implementations, as you can see, are not yet very easy to get to work together in the same process. Our socket is a great technology, but unfortunately, documentation is very limited. I asked some things online and I got help from the helpful contributors, but mostly pointing to the examples online, which are certainly useful, but then again, limited, and you have to do a lot of work to figure things out as you go. I also didn't like very much that the Java implementation relies on Project Reactor, because you might simply not want that. You might want to use a different implementation. And if you are in a Spring sort of world, this is perfect. It is absolutely perfect for you. It will just mix seamlessly with Spring Boot. In fact, there's books written about it. But if you don't particularly like Project Reactor, you're still stuck with it. So it's just a dependency. In fact, my conclusion is that, in fact, while not built for this streaming purpose, if you mix HTTP with some underlying streaming semantics, and there are some projects that have done that, like Akka HTTP, well, this solution might be a more efficient and faster way for you to modernize your legacy application. And this is all for me, and maybe we can have share some conclusion together with Mary at this point.
Sure. Yeah. Thank you, Fabio. It's a great demo and very clearly explained. Thank you. So yeah. And yeah, we're kind of looking at this whole pipeline and we're wondering, yeah, this is like a sample implementation. Could we actually have other implementations? I think as you mentioned about, right, we could actually write maybe the legacy processor too, could be like in Python, in even JavaScript, maybe Node.js.
For sure.
So I think it basically we're trying to illustrate is that with the reactive streams kind of approach, it's actually make your application a lot more modular, so to speak, like modularize. If you're writing
Correct.
microservices, you can actually have the legacy processor as one microservice and the other legacy processor is another one. And so you can see that they all connect with each other through messaging. And in this case, we, as Fabio has illustrated, it will be in our socket and you can plug different things in, plug and play. So it's actually a very flexible approach. And that's what we also like about our reactive. And it's because of that capability that kind of enables us to do things more efficiently too.
Indeed.
So yeah,
Yep.
exactly.
Indeed.
So yeah. And then also maybe one last kind of conclusion is that, well, how about like Project Loom that's kind of scheduled now for Java 18, I believe. And
that's right.
So there's still a couple more versions before it will be released. But we wonder, right, with virtual threads, carrier threads too, right? And we wonder how, how it would be. And I've also like heard about people talking about, oh, Project Loom's coming out, Reactive's gonna be dead. But I
Yeah,
don't think so, right? I mean, Reactive, so to speak, we're handling the problem domain on a different level, on a more abstract level, but the virtual threads are a bit more of the lower level, dealing with more of the towards more of the primitive kind of more threading kind of that direction. So then it's more like
exactly.
they both should be complementing each other is what I'm thinking.
Exactly. I fully agree. I think Project Loom is definitely going to be a very, very powerful uh, addition to the JVM. In my personal opinion, I think is going to be very useful for low level logic. So maybe if you are a library maintainer, or well, maybe if you're the maintainer of one of these reactive library
Yeah,
yourself, this is going to be really, really useful.
yes,
But for a lot of users, simple users of these libraries,
yeah,
I think we will still prefer to operate at a higher level than going back to creating and spinning up threads ourselves, even if they're virtual. We'll
that's right.
see. We'll see how it plays out. But yeah, certainly something to definitely keep an eye on.
Yeah, very true. Yeah, wonderful. Yeah, it's been a great conversation too in our presentation. Hope everybody enjoys it. And
Yeah, these
yeah,
are a couple of links to lots of things we've mentioned. The first one is the sample code that I've shown you. Our socket, Quarkus, Docker, lots of technologies that we mentioned. And I believe this is all from us. So thank you very much. These are our contacts and our links.
that's right. Yeah. Thank you all for attending our talk.
Yeah. So yeah, goodbye everybody, and
Yeah.
till the next
Bye.
time.
Yes.
Bye.
Bye bye.